So, for example, let us prove that E of x is equal to its Maclaurin series. So this is exactly the missing component of example 1, right? In example 1, we said, let's say e to the x can be represented by power series. Example 2 shows that indeed this is the case. Because e to the x is equal to its Maclaurin series, it obviously can be represented by the power series, by the Maclaurin series. And so we are going to do this using the remainder estimate. So let us say we want to look at the difference at the remainder of order n. Then by this discussion, we need the derivative of order n plus 1 of f. And of course, it is e to the x. Because the function being e to the x means all of its derivatives are e to the x. So say we're looking at this function, then on the interval x minus 0, absolute value at most d, right? So this plays the role of x minus a at most d over here. We have that the absolute value of the n plus first derivative, we must bound it by a constant. And so what we'll do is we'll bound the n plus first derivative by its maximum. So we are looking at the interval. For some positive d, we consider the interval between minus d and d, and here is the 0. And so we're looking at this interval. This interval, we have our n plus first derivative, e to the x. So the graph of e to the x is something like this, right? So clearly we have a positive function which is increasing on the interval from minus d to d. So to estimate the absolute value of this n plus first derivative, as we're supposed to according to the remainder estimate, we'll just take the maximum value of the n plus first derivative, the maximum value of e to the x on this interval, which is, of course, e to the d, right? So we have a positive function which is increasing, which means it attains its maximal value at the right endpoint of this interval, at d. And so at that point, it is equal to e to the d. And so that is the maximal value of absolute value of fn plus 1 of x. So this number here will be our m. Right? And we therefore see that we have control over the n plus first derivative of f, exactly as we need for the remainder estimate. Then, by the remainder estimate, or Taylor inequality, if you wish, we have that absolute value of f of x minus Tn of x, so maximal value of f minus the nth degree Taylor polynomial, is the absolute value of the nth remainder, is at most and now we're using this formula over here, is at most m, so e to the d, divided by n plus 1 factorial times x minus a to the power n plus 1. Now our next goal would be to show that this expression goes to 0 when n goes to infinity. So we need to show that the remainder goes to 0 when n goes to infinity. Since then, the nth degree Taylor polynomial goes to f, and we are done. So how do we do this? Well, the remainder estimate tells us that this inequality is true for x minus a at most d. If you look here, this is the interval that we work with, and the conclusion of the remainder estimate also holds on this interval. Since we are only talking about x minus a, about x minus, well, in this case it's 0 in fact, about x minus 0 being at most d, we can estimate this factor over here. So we have absolute value of f of x minus Tn of x is the absolute value e to the x, that's our function, minus Tn of x. So that is at most e to the d divided by n plus 1 factorial multiplied by d to the n plus 1. Right, so this distance here from 0 to x can be at most d, because if x changes on the interval between minus d and d, distance from x to 0 can be at most d, of course. And so we replaced the factor absolute value x minus 0 by its maximal possible value. And if we can show that this goes to 0, then we are done, right? Because then this is the maximal value of the difference fx minus Tn of x on an interval like that. So if we can show that the maximal value of this difference goes to 0, then Tn of x goes to f of x on every point on our interval between minus d and d, and then that is precisely what we want. It means on any interval, our function is the limit of the partial sums of the Taylor series. And so it remains to show that the limit when n goes to infinity of this expression is 0. So note d is any fixed positive number. So how do we show this? Well, in this product, only the d to the power n plus 1, and the n plus 1 factorial depend on n. So we can take the e to the d outside the limit and only care about the other two terms. So let us work with the limit. N goes to infinity, d to the n plus 1 divided by n plus 1 factorial. How do we show that this limit is 0? Well, let us think about the quotient we are dealing with here. We have d to the power n plus 1 in the numerator, which means we have n plus 1 factors, each of them equal to d in the numerator. So here we have n plus 1 factors. Similarly, we have n factors in the denominator, but they vary from 1 to n plus 1. So they go like this: 1, 2, blah, 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 up to n plus 1. So we have n plus 1 factors as well, except that they range from 1 to n plus 1. So what we should do now is to group our factors in this way, so that we have a product of n plus 1 fractions. So we rewrite the limit as the product d over 1 times d over 2 times blah 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 times d over n plus 1. D is a fixed positive number. So let's say now that d is less than some integer n0. So we have some integer such that d is less than this integer. Okay. Then our limit will eventually contain more than n0 factors. In fact, it will contain more than 2n0 factors. So let us say for very large n, we'll be looking at very large number of fractions multiplied. All their numerators will be equal to d. So the picture will be like this. We'll have d over 1 times d over 2 times blah 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 times. Then we will have, at some point, we'll have the denominator reach 2n0. Right? It is a positive integer, and therefore the factorial will contain such a factor. Then we will have the factor d over 2n0 plus 1 and so on, d over 2n0 plus 2, blah blah blah, up to d over n. So for sufficiently large n, we can talk about such products, because then n is bigger than 2n0, and this is what the product of n plus 1 factors will look like. Okay, what can you say about this product? Well, it contains n plus 1 factors total, n plus 1 fractions are like this total. And what do we know about these fractions? Well, we have some number of fractions, specifically 2n0 factors here. Let us multiply these 2n0 factors and say that their product is equal to some number, right? It is finitely many terms, so their product is also finite. No matter how many finite numbers you take, if you multiply them, you get a finite number, assuming that the number of factors is finite, which it is. Okay? And then we have some number of fractions, specifically n minus 2 and 0 factors. What do we know about these? Well, we have first the 2 and 0 factors, which all after multiplication give us 2. And then we have d over 2 and 0 plus 1 times d over 2 and 0 plus 2, and so on. So the interesting thing about this product is that since d is less than n0, we also have that, say, all this first fraction is less than 1/2. And all this second fraction is also less than 1/2. And the same holds for all the rest of them up to this fraction here, which is also less than 1/2, because d being less than n0 means that the numerator is at most 1/2 of the denominator, and it holds for every fraction in this product. So we will have a limit of a constant number a multiplied with something that is less than 1/2 to the number n minus to the power n minus 2 and 0. Okay, so we're looking at the limit of this product. And what we did was split away some number of factors up front, and we said they multiply to a finite number. And then we have a growing number of factors at the tail of this infinite product. Each of these factors is at most 1/2, and we have a growing number of them, right? We have n minus 2 and 0, which is still going to infinity when n goes to infinity. So we have 1/2 to a power that goes to infinity. And so evidently the value of the product of all of these terms being less than 1/2 to this power and at the same time positive will go to 0. And so we have a fixed finite number multiplied by something that goes to 0. Therefore, the entire limit is 0. So let's see what we have obtained here. So we set out to show that this product is 0, and we were successfully able to show this. And this, by the remainder estimate, means that the difference between f and the nth partial sum of the Taylor series, aka the remainder, goes to 0 when n goes to infinity. So this is precisely what our discussion demonstrates, right? We took the difference, the Rn of x, we estimated it by this number, and then we showed that this number goes to 0. The right-hand side over here goes to 0. Therefore, by the remainder estimate, we have that the partial sums of Taylor series for e to the x go to f of x for absolute value of x less than d, less than or equal to d, and this holds for any positive number d. Hooray! since d is any positive number, this means that for any x, Tn of x goes to f of x, right? The nth partial sum of the Taylor series goes to its function, e of x. And so we have showed that e of x is equal to k from 0 to infinity, x to the k divided by k factorial. Something that we were previously forced to just assume without justification. Now we have rigorously established that this function is indeed given by this power series representation. And that is because of the remainder estimate. We have shown that the remainder, the difference between function and the nth partial sum of the Taylor series, of the Maclaurin series in this case, goes to 0 when n goes to infinity. And that allows us to justify this formula here. So this is a very important representation, both because of the importance of the function e to the x and due to the convenience of this series. This series converges very quickly. So as I already mentioned, you can use it for any computational purposes. When you need e to the x, you can approximate it very well by the value of this infinite power series. And in turn, you can approximate the value of the infinite power series by picking a suitable truncation, by picking a suitable finite partial sum of this power series.